All right, we've got some work to do if we want to prove that triangles are similar. So we're going to list any pair of corresponding equal angles, pairs of sides, in a given ratio. We've got to give reasons at each step. We've got to write a similarity statement like this. For example, triangle ABC is similar to triangle DEF, and the order of those points matters. And we can also write it the other way. And then we want to write out the test that we use. So the similarity test in abbreviated form: side, 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 angle, 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 right angle, hypotenuse, side. And to apply similarity in practical problems, we're going to prove two triangles are similar first, as we did before. But then we're going to find the scale factor, and then we're going to nut out the values of any unknowns. So let's start first by proving that each of these is similar. Now, it may look a little bit confusing, they're a little bit flipped around, but we have the joy of understanding how our angles work, especially when we have parallel lines, as we do from A to B and D to E. They are parallel to each other, and we're going to use that. We're going to prove that. But firstly, we're going to note that here, this angle at C, on both sides, these are vertically opposite angles, so they're going to be equal to each other. Angle ACB is equal to angle E, and I'll show you why we write E first, C in the middle, D, because actually A and E are also going to be equal to each other. I'll use another symbol, put a little X there. Angle B, A, C is equal to, I should have put here vertically opposite, pardon. BAC is equal to angle DEC, because these are actually alternate angles if we have parallel lines. So we want to add that DE is parallel to AB. And again, it's important that we have the A in the middle, and we start from the right way around. So it looks like B and D will match up. So once again, we've got another set of alternate angles there. So they actually relate to each other in the same way. So we would put angle, what have we not got? A, B in the middle, C, is equal to angle E, which corresponds to A, D, which corresponds to B, and C. And the reason is exactly the same thing. Alternate angles, and D and E, DE and AB are parallel to each other. So we round that out, we nut that out, and we say, therefore, triangle in this order is important. A, B, C. Remember that A corresponds, and I'll put the sign in a second, and E corresponds to A. B and D are equal to each other. C and C, of course, are equal to each other because they're vertically opposite. So therefore, these triangles are similar to each other. And the way we can prove that is angle, angle, and our friend angle. That's how we've worked that one out. And for example B here, it may not look like it, but we do have two similar triangles. One is this little itty bitty fellow here who's inside the larger one. The first thing I'm going to tell you is that both of these triangles have an angle in common, and that's angle C. So in my mind, I am going to do a little flipper-doodah and take little Mr. Inside triangle. I'm going to keep that angle at C the way that it is, and I'm actually going to put B up here, and I'm going to put D over here, and that's how it corresponds to A. And I'm going to hopefully prove to you how I've done that. So let's go back to the beginning. So let's look at the scale factors here. So if we want to find a scale factor, if we want to try and think that DC, which is 6, and EC, scale factor of 2, well, maybe, but then if we try and look at BC and AC, 4 times 2, it doesn't work. So let's look at it another way, since we've done the flipper-doodah around. Actually, if I look at, so DC and AC, you can see how I've flipped it and it works that way. Let's prove it by saying, well, 6 times 3 is 18. That looks like those sides correspond to each other. And then if that's the case, then BC, this one, should correspond to EC times 3 as well. So we found our scale factor. So let's just write it out properly. AC, which is equal to 18, over the original DC, let's call it the original, doesn't really matter as long as we do it in the right direction, that gives us that scale factor of 3. And what I said before is we've got something in common. Angle C, even though I don't need to flip that inside triangle around for angle C to be the same. So we know that angle ACE, which is the big triangle, the image, shall we say, and angle DCB, which is the wee little triangle, which I redrew out there, they are common to both triangles. So they'll be equal to each other. So we got sort of a side relationship. We've got an angle that equals each other. So if we can build up another side relationship, EC, which we said before, should be, what is EC equal to? 12, over the original of BC. That's how they relate, and you can see EC and BC when I flipped it over, and that is what, equal to 4. So again, we've got our scale factor of 3 here. So therefore, we can prove that triangle, there's my triangle symbol, ACE, is similar to triangle ADCB. And that's how they relate to each other. And what's our proof? Side, angle, side. Chris's shadow, 1.2 meter long, while a 1 meter vertical stick has a shadow of 0.8 meters long. First one's easy. Give a reason why the two triangles are similar. Now, we know that we have a common point. We know that the sun is coming from the same place. So we're going to see that not only do we have a right angle, but the sun is coming from the same direction. It's going to give us that this angle is the same. And then we can assume that because those two angles are equal on each similar triangle, that the other unknown is going to be equal as well. So our reason is that all angles are the same, or angle, angle, angle. So now we want to try and figure out Chris's height from what we know. So let's see if we can figure out what the scale factor is. The scale factor, we've got to compare two similar sides. So we know for Chris that we're going to end up with the image of 1.2 meters over the original, shall we say, of 0.8. And that gives us a scale factor of 1.5. I'm going to write it another way for you. If I multiply both of those by 10, does that make your life a little easier? It's the same dealio, right? So that's our scale factor. So using that scale factor, all we have to do is to give Chris's height, back in my day, we didn't add that extra S, but talk to your English teacher, I think we do now, is 1 meter. So we want to try and find what that is. 1 meter times the scale factor of, say, 3 over 2, you can do 1.5. So therefore, Chris's height is 1.5 meters. There you go, buddy. Good work.